So this set of review notes is on polarity, and at the end I'm also going to provide you the answer key to the polarity worksheet. But that polarity is a measure of how the atoms in covalent bonds and also covalent molecules, how they share their valence electrons. And remember that polarity is actually determined by the electronegativity difference between the atoms in the bond. So here's the chart of electronegativities, and as you remember, electronegativities increase as you go left to right across a column, across a row, and they increase also as you go up a column, or they decrease as you go down a column. So the most electronegative element, of course, is fluorine, and the least one is francium or francium. And just remember that electronegativity is really just a measure of how likely something is to gain an electron. So of course, these guys over here with 7 valence electrons are going to want to gain much more than these over here with just 1 valence electron. So therefore, electronegativity increases kind of as you go up and to the right of the periodic table. So as I said, there are two kinds of polarity. There's the polarity of bonds, and then there's overall molecular polarity. When we're talking about the polarity of chemical bonds, we're really just talking about which of the two atoms in the bond wants the electrons more. So we have these two ways to classify, we have 3 ways really to classify bonds. And we saw this already. We have ionic bonds, and we have covalent bonds. Spelled that C wrong. And within the covalent bonds, we have 2 kinds. We have what we call polar covalent bonds, and we also have what we call non-polar covalent bonds. So these are actually determined by electronegativity differences between the atoms. In a non-polar covalent bond, the electronegativity differences are between 0 and about 0.4. In polar covalent, it's between about 0.4 and about 1.9. And then anything that's greater than 2 electronegativity difference is an ionic bond. But the bigger thing you should know in a polar covalent bond, electrons are shared unequally between the atoms, and in a non-polar covalent bond, the electrons are shared completely equally between the atoms. Which means in a non-polar covalent bond, there's no charges, and in a polar covalent bond, you get very slight charges on the different atoms, and I'll show you what this means in a second. Consider the polar covalent bond between hydrogen and oxygen. You see this bond all the time in water. So there's hydrogen, and there's oxygen. We'll just draw a water molecule here, and we'll just draw another one. Sorry, I did not put this in the bent shape. That's possible. If I am looking at electronegativities, oxygen has electronegativity of 3.44, and hydrogen has electronegativity of 2.20. Put these numbers down. So this is between 0.4 and 1.9, so it's definitely a polar covalent bond. Obviously, oxygen has a much higher electronegativity, so the electrons that are shared in this bond right here and in this bond right here, they're going to spend more time around oxygen. So what ends up happening is oxygen ends up getting this slight negative charge, and each hydrogen ends up getting a slight positive charge. And this weird symbol, of course, is the Greek letter delta. So this is what's going on within a polar covalent bond. And later on, we'll talk about how this makes a polar molecule. But right now, know that this is what happens with the electrons shared in a polar covalent bond. So if you have 2 atoms, we're not talking about molecules here, just 2 atoms, how do I know if the bond is polar or non-polar? Remember, we had a set of rules, and the easiest thing to do is just remember the ones for the non-polar molecules. So it's non-polar if the bond is between the following: 2 of the same. What do I mean by 2 of the same? Sometimes we have these diatomic molecules like O2 or N2 or H2. Because they're both the same atom, neither one is going to want electrons more, so it's definitely nonpolar. The other ones you need to know are any bond between C and H is nonpolar. C is actually 2.55, H is 2.20. It's a very common nonpolar. They're 0.35 apart. And finally, any combination between the elements C, S, and I. So C actually is 2.55, S is 2.58, and I is 2.66. They're all very, very close to each other. Selenium and sulfur are in there too, but these are the ones you should really know. The C, S, and I combination, any combination, so CS, Si, or Ci, any of these bonds will be nonpolar. Everything else is polar. So if it's not either this, this, or this, then everything else is polar. And that's how we do a polarity of bonds. Of course, polarity of bonds also determines polarity of molecules. So for example, let's say I have the compound methane, which is CH4. If I were to draw this, it would look like this, tetrahedral molecule. But each of these bonds is nonpolar. So because there's no direction on the bond, the whole molecule ends up being nonpolar. Whereas if I have the compound HF, hydrogen fluoride, it looks like this, fluorine is much more electronegative. So this bond is polar. And the way we show a polar bond is we draw the arrow, the dipole arrow on top. The plus sign goes to the positive atom, the arrow goes towards the negative atom. And this whole molecule is going to be polar because there's a polar bond. Sometimes, however, you run into a situation where even though the bonds are polar, the molecule itself is nonpolar. And let me show you one. So this is the molecule CF4. Fluorine is the most electronegative. I'll put the lone pairs on there, just so we do this properly. The thing is, each one of these bonds is the same strength, and the molecule is symmetrical. So because the molecule is symmetrical, this one and this one cancel, this one and this one cancel, and so we say this molecule has polar bonds, but we also say that it's a nonpolar molecule, and so that's a big difference. So how do we know that the molecule is polar or nonpolar? Here are some clues. So how do I know? The molecule is going to be nonpolar under the following conditions. It's got to have all the bonds are nonpolar, or the molecule is the same bonds but symmetrical. So like a tetrahedral molecule or a linear molecule, those are symmetrical. And there have to be no lone pairs on the central atom. So if all these things fit, it's definitely nonpolar. A polar molecule, the biggest getaway is that it's not symmetrical. Any molecule is not symmetrical. Or if it has lone pairs on the central atom, then it is going to be a polar molecule. And so here's the worksheet I gave you. It's just the review of the previous worksheet, but I'm going to provide you the answers. So here's the first worksheet. We're going to do the compound HI. When I draw the Lewis structure, it looks like this. So there's no central atom and there's no unshared pairs. This molecule, because it has two atoms, we're going to say it's a linear shape. Still no idea what this Ti column means. If I look at my chart, it's not a CS or I combo, so the polarity of bonds, we're going to say the bonds are polar. And because this molecule is not really a symmetrical molecule, the molecule itself is also polar. And if we were to draw the dipole, and I'm going to do this with a highlighter so you can see it, the dipole is going to go this way towards I. The next molecule is CBr4. Sorry, I got to switch to the pen here. So there's C, Br, Br, Br. There's not a ton of room here. This molecule has 4 atoms bound to the central atom and no unshared pairs. This molecule is tetrahedral. It's hard in the worksheet. The bonds themselves are actually polar, but the molecule, we're going to say it's NP for nonpolar. This is because it's symmetrical and everything cancels. So if I were to draw this, and this cancel, and this cancel. So there is no molecular dipole. H2S. S is actually going to be the central atom. This is going to look very much like water. There's H and there's H. There are 2 atoms bound to the central atom and 2 lone pairs. This is a bent molecule. This HS bond is a polar bond, and the molecule itself is also polar. And if I were to draw the molecular dipole for this, it would be pointed towards the S, just like that. HCN is kind of a weird one. Let's get back to the pen. HCN is H to C, triple bonded to an N. There's 2 on the central atom and no lone pairs. This is a linear molecule. However, because we have kind of this weirdness at play where C is bonded to 2 different atoms, you have kind of 2 different strengths in terms of polarity. You have the C-N bond, which is nonpolar, so that's nonpolar for C and N. But you have the polar bond, C and H is nonpolar. You have the polar bond between C and N. So what ends up happening is this molecule ends up being polar because everything is pulled in this direction towards the N. So that's kind of a tricky one. And then CCl4 is just going to be very much like CBr4. It's one of those completely symmetrical tetrahedral molecules where the bonds are polar. 4 and 4, tetrahedral, but the molecule itself is nonpolar, tetrahedral. And so this is polar bonds and nonpolar. So this is the last page of the worksheet. We'll just do these SF2. SF2 has sulfur, lone pair, and sorry, I did this wrong. A lone pair bonded to 2 Fs. I didn't draw this perfectly right, but no, it's 2 and 2. So this is a bent molecule. This bond is going to be polar, and so is the molecule, because the molecule is bent, and actually the polarity is going to be away from the S because of that. PCl3 is kind of a tricky one here. Let's do some blue. There's P. Cl, Cl, Cl. And there's three bonded to the phosphorus, 1 lone pair. This is actually trigonal. This is trigonal pyramidal. Ti, this whole column I'm going to cross out. The bonds themselves are polar, and the molecule is polar, and the polarity, we'll do this in red so you guys can see it. The polarity actually is going to point kind of towards this C right here, in the Cl right here in the middle, because everything is pulling down off that C. CH3Cl is another one of those weird ones. We're going to put an H, an H, an H. Those bonds are all nonpolar, but Cl itself is a polar bond, so we've got 4 and 0. It's another one of our tetrahedral molecules. The bonds themselves are nonpolar and polar. Remember, CH is nonpolar, CCl is polar. This molecule is going to be polar, and everything is going to be pulled towards the Cl. Whatever side you put the Cl on is fine. CH2S, this is a good one. This is a good, tricky one for you guys. It's going to look like this. C is in the middle, S is up here with its lone pairs. There's an H, there's an H. It's 3 and 0. This is actually trigonal planar. I just wrote trigonal like I didn't know what I was doing. Trigonal planar. The bonds are all nonpolar. The molecule itself, if you said nonpolar, it's fine. It's actually going to be a weirdly polar molecule. And the reason being is it's not symmetrical, and this double bond is shorter, and there's some weird lone pairs in there. I wouldn't expect you to know this, but if you said it was nonpolar, that's fine, but there is actually a polarity going that way. And finally, SCl2 is going to be exactly like SF2. This is going to be your 2 and 2. It's your bent, and everything is polar in the exact same way. We'll do this in red so you can see it. So there's your worksheet. Good luck. This is not an easy topic. Just remember, separate the polarity of bonds first, and then figure out the molecule.